Walk any refinery or petrochemical unit and you are looking at thousands of pressure-containing items. Vessels, columns, exchangers, tanks, kilometers of piping across the racks. Every one of them is degrading, quietly, right now. And every one of them is asking for the same thing, inspection. But you do not have unlimited inspection hours, unlimited scaffolding, or unlimited shutdown windows. So which one do you look at first? Get that wrong, and you lose containment. That question is exactly what risk-based inspection answers. RBI does not rank equipment by age, or by habit, or by whichever item is easiest to reach. It ranks by risk. And risk has two dimensions: the probability that a component fails, driven by the damage mechanisms actually acting on it, multiplied by the consequence if it does fail. Plot probability against consequence and you get a risk matrix. High probability, high consequence sits in the red corner, and that corner is where your inspection effort belongs. For decades, inspection ran on the calendar. Every vessel on a fixed interval. Every line on a fixed interval. It is simple and it is auditable, but it treats a hot hydrogen line and a cooling water line as though they were the same asset. They are not. They see different damage mechanisms, at different rates, with wildly different consequences. So a uniform interval over-inspects assets that could never hurt anyone, and under-inspects the few that can. It spreads effort evenly, and leaves blind spots exactly where you cannot afford them. So what is RBI? API Recommended Practice 580 sets out the elements of a risk-based inspection program. It is a systematic process linking four things: the equipment and its operating conditions, the credible damage mechanisms acting on it, the effectiveness of the inspection you actually perform, and the safety, environmental and business consequences if containment is lost. It can be run qualitatively, on engineering judgment in broad categories, semi-quantitatively, blending scoring with calculation, or quantitatively, as in API 581, where probability and consequence are computed. And it is a team activity: inspection, materials, process, operations, and HSE, never one engineer with a spreadsheet. The workflow follows a consistent path. First, scope the study and build the inventory, units, systems, corrosion circuits, and equipment tags. Second, review damage mechanisms, what can actually degrade this component, in this service. Third, assess probability of failure. Fourth, assess consequence of failure. Fifth, combine the two into risk, and rank the whole population. Sixth, build the inspection plan, method, coverage, location and timing, against a risk target. Seventh, manage what is left over, through monitoring, repair or process change. And eighth, reassess, because a risk ranking is only true on the day you calculated it. Step 2 carries most of the technical weight, because you cannot assess probability without naming the mechanism. In refining and petrochemical service, the usual suspects are described in API 571. Internal thinning from corrosion or erosion. Corrosion under insulation, which hides beneath the jacket until it is severe. Environmental cracking, such as chloride stress corrosion cracking or wet hydrogen sulfide damage. High temperature hydrogen attack in hydroprocessing service. Creep in furnace tubes. And mechanical fatigue at vibrating small bore connections. Name the wrong mechanism, and every number downstream of it is wrong. Probability of failure is not a guess about bad luck. It asks whether this component is susceptible, how fast the damage is progressing, how much life has already been consumed, and, critically, how confident we are in that answer. Inspection history is part of the calculation. In the quantitative approach of API 581, probability is a generic industry failure frequency, adjusted by a damage factor that grows with time and service, and by a management systems factor. Note what this means: effective inspection does not slow corrosion down. It reduces your uncertainty about how much corrosion is already there. Consequence of failure asks a completely different question. If this component leaks, what actually happens? Consequence is judged across several dimensions: harm to personnel, environmental release, damage to surrounding equipment, and lost production. It depends on what is inside the inventory available to release, whether it is flammable, toxic, or benign, the pressure driving that release, and how quickly the leak can be detected and isolated. API 581 works this through a set of hole sizes, from a small leak up to a full rupture. Now the part that programs get wrong most often. Not all inspection is equal. API 581 grades inspection effectiveness from highly effective down to ineffective, and the grade depends on whether the technique matches the damage you are hunting. Ultrasonic thickness readings are excellent for wall loss, and effectively blind to a tight surface crack. Magnetic particle and penetrant testing find surface breaking cracks, and tell you nothing about internal thinning. Coverage matters as much as method. A handful of thickness points is not the same as scanning the corroded region, and an inspection you cannot physically reach earns no credit at all. Take 3 illustrative assets. A high-pressure hydrocarbon line near a unit battery limit, with a measured thinning history. High probability and high consequence, because of a large flammable inventory close to occupied areas. It lands in the high-risk corner. B a low-pressure utility water line. It is corroding too, but a leak is a puddle, not an event. Low consequence pins it to the left-hand edge, in the low-risk band, whatever its corrosion rate. C an atmospheric storage tank, degrading slowly, so lower probability, but with a serious environmental and economic consequence. It sits in the middle of the matrix. Spread the same effort evenly, and you protect nobody. So how does this actually make a plant safer? RBI finds degradation before it becomes loss of containment, on the equipment where loss of containment matters most. It turns a turnaround from a wish list into a ranked plan, so limited shutdown hours go to the equipment that has earned them. It connects to the rest of integrity management, integrity operating windows, which tell operations when a process excursion has changed the damage picture, corrosion control documents, management of change, and fitness for service under API 579 when a flaw is found. And it makes risk visible to management, in the same language as every other business risk. RBI does not replace design codes, operating discipline, or emergency response. It aims the effort. Some warnings. RBI is not a paperwork exercise. A study that never changes an inspection plan has achieved nothing. Do not copy intervals from a similar unit without confirming the mechanisms are the same. Do not take credit for an inspection that could not have found the damage or could not reach it. Update the study after process changes, after failures, and after every significant finding. API 580 calls this evergreening. And be clear about what a low ranking means. Low risk today, on today's assumptions. It is not a certificate of safe forever. Risk-based inspection is a simple idea, executed with discipline. Understand what can degrade. Judge how likely it is, and what it would cost. Rank it honestly. Then inspect the right equipment, in the right place, at the right time, with a method that can actually find the damage and update the picture as the plant tells you more. That is how inspection stops being a routine, and starts being a safety barrier. Jarasa Consultation Services. Integrity, inspection, reliability.